Hello, everyone. So last time we looked at a system of differential equations, first order system of differential equations. So we wrote it in the matrix form, if you remember. We considered x prime equals ax, where x is n by 1 vector, a is n by n. And we can write x as, let's say, x1 to xn, and xi here are unknown functions. And we can assume that these are functions of t, and t is our independent variable. And we saw that this system has n linearly independent solutions. N linearly independent solutions, and the general solution is a linear combination of linearly independent solutions. So once you find linearly independent solutions, to find the general solution, you can simply consider linear combination of those linearly independent solutions. Linear combination means what? Means a constant, arbitrary constant times the first solution plus another arbitrary constant times second solution, and so on. Now, we saw a recipe to find linearly independent solutions in at least one particular case, where the matrix A has n distinct eigenvalues, n distinct real eigenvalues. So we saw if A has n distinct eigenvalues, let's say R1 to Rn, with the corresponding eigenvectors, let's say C1 to Cn, then what we claimed was that then C1 e to power R1t all the way to Cn e to power Rnt are n linearly independent solutions for x prime equals ax. So let's see whether we can prove this fact, proof of this fact. So here I have n solutions, C1 e to power R1t all the way to Cn e to power Rnt. So each solution, because here we are dealing with a vector, our unknown is a vector. So each solution is a vector as well. So C1 and to Cn are also vectors. So this C1 is a vector times e to power R1t. So this is not a vector. This is a number times a vector. It will give me a vector. So this is a vector. It's a function of t. This part is a function of t. This part is not a function of t. It's a fixed vector. Overall, it's a function of t. And overall is a vector because this part is a vector. This part is a number. So one part includes dependency on t. One part includes makes the solution a vector. This part makes it a vector. This part makes it a function of t. So here I have n solutions, and I want to show, or my claim is that these are linearly independent. Now, how can I show that? few vectors, in this case, few solutions are linearly independent. I have to assume that some linear combination of them is 0, and then I have to show that each coefficient must be 0. So suppose that, or let's say beta 1 e to power beta 1 times the first solution, which is C1 e to power R1t all the way to beta n Cn e to power Rnt equals 0. So if this is 0, this is 0 is going to be 0 for every t. When we say 0 here, we mean constant function 0. So if this is constant function 0, then it has to be 0 for every t. Then we can replace, this is true for every t. So then we can replace t with 0, and then we get beta 1 C1 all the way to beta n Cn equals 0. Now here C1 to Cn are eigenvectors corresponding to distinct eigenvalues R1 to Rn. And last time I mentioned that in Math 252 in linear algebra, you have learned that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So from last time, we know that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So that means C1 to Cn are linearly independent. So if C1 to Cn are linearly independent, and if some linear combination of them is 0, then that means every coefficient must be 0. This is exactly the meaning of linear independence, that if some linear combination is 0, and if the vectors are linearly independent, then every coefficient must be 0. So here we have beta 1 C1 all the way to beta n Cn equals 0. So that means each beta I should be 0. Each beta I has to be 0. And that means our solutions, which were C1 e to power R1t all the way to Cn e to power Rnt are linearly independent. And it also means that the general solution can be written as linear combination of these solutions. Once we verify that these solutions are linearly independent, because we have n of them, then every solution can be written as a linear combination of these solutions, meaning that a constant times first solution plus another constant times second solution, all the way to another constant or nth constant times n solution. So we can say that note that the general solution, in this case can be written as follows. Let's say beta 1 C1 e to power r1t all the way to beta n cn e to power rnt. And here beta 1 to beta n are constants or arbitrary constants. And how do we find these constants? Once you write the general solution in this form, then to find the constants, we need to simply use the initial conditions. So these constants can be found using the initial conditions. We looked at an example last time. If you remember, it was x prime equals ax with with a equals, the matrix was 1 2 3 2. So we found last time, we found the linearly independent solutions of this system. Because the matrix is 2 by 2, we need two linearly independent solutions. And they were, so eigenvalues were 4 and 1. And eigenvectors, one of them was 2 and 3. So 2 and 3 e to power 4t. And the other one corresponding to eigenvalue of -1. The eigenvector was 1 and -1, corresponding to lambda equals -1. So the other solution, the other linearly independent solution was 1 and -1 e to power -t. Now let's say, find the solution of the system above, with the initial condition. Now let's add the initial condition to our problem, and then that helps us to find the coefficients in linear combination. So let's say the initial condition is x of 0 equals 0 and -4. 0 and -4. So the general solution here, we just said that the general solution is the linear combination of linearly independent solutions. And linearly independent solutions are these two solutions. So like I said, the general solution is beta 1, 2 and 3 e to power 4t plus beta 2. So let me say x of t equals this. Beta 1 this plus beta 2, 1 and -1 e to power -t. Now to find beta 1, beta 2, we just mentioned that we have to use the initial condition. So we know that x of 0 is 0 and -4, which is going to be beta 1 times 2 and 3 plus beta 2 times 1 and -1. Now, if I simplify this, I can write this one as 2 beta 1 plus beta 2 and 3 beta 1 minus beta 2 is equal to 0 and -4. So we can say that 2 beta 1 plus beta 2 equals 0. 3 beta 1 minus beta 2 equals -4. So this will give me beta 2 equals -2 beta 1. If I replace it here, then I'll have 3 beta 1 plus 2 beta 1, because it's minus beta 2, and beta 2 is -2 beta 1. So it's going to be plus 2 beta 1 equals -4. So that gives me 5 beta 1 equals minus 4. Beta 1 equals minus 4 over 5. And then beta 2 will be minus 2 times beta 1. That's going to be 8 over 5. And then the solution, so what will be the solution then? Well, we had beta 1 times the first solution plus beta 2 times the second solution. So then we will have x of t equals minus 4 over 5 minus 4 over 5, 2 and 3 to power 40, and then plus 8 over 5, 1 and minus 1, e to power minus t. So if we compare it with this one, it's beta 1, 2 and 3 to power 40 plus beta 2, 1 and minus 1, e to power minus t. We already found beta 1 and beta 2. So we just needed to substitute back, and we got the solution this way. We can also write this as x1 of t and x2 of t, because this x of t that we have here is x1 of t, it's a vector. The first element is x1 of t, the first unknown function, and the second element is x2 of t, the second unknown function. So x of t basically here can be written as x1 of t and x2 of t. So x1 of t is not vector anymore, so it's just x1 of t and x2 of t. And therefore we can write this one as x1 of t equals minus 8 over 5 e to power 4t plus 8 over 5 e to power minus t. And then x2 of t will be minus 12 over 5 e to power 4t minus 8 over 5 e to power minus t. We expand the right-hand side, minus 4 over 5 times 2 is minus 8 over 5 e to power 40 plus 8 over 5 e to power minus t. That's the first coordinate of this vector, which is supposed to be equal to x1 of t, the first coordinate of the left-hand side. And similarly, the second coordinates are equal, so x2 of t will be equal to this expression here. So this is how we find the solution, the general solution or the unique solution in the case of having the initial values. In the case where the matrix has n distinct real eigenvalues. Now we want to look at the concept of phase portrait. So phase portrait. So I will cover the other cases where, you know, the matrix does not have n distinct eigenvalues later. But for now, let's also learn about phase portrait applied for this case that we already learned, and then we will move on to the next cases. So remember, what is the equation that we consider? So given x prime equals ax, okay, so we want to, and let's say with some initial condition, with let's say x of 0 equals b, we want to find out the behavior of the solution, let's say x of t, as t goes to infinity, without solving algebraically, or finding x of t algebraically. Finding x of t algebraically. We only want to use the graph to find out how the solution behaves as t goes to infinity. So here, basically, remember x is has two coordinates, x1 and x2. So we are going to denote them with we are going to let each axis represent one of these coordinates. So I have x1 axis and x2 axis. So this is basically x1, x2 plane. So x-axis represent x1, the first coordinates, and y-axis represent x2, the second coordinate. Here we have two unknown functions and two coordinates. So right now I'm focusing on the case where everything is 2 by 2. So the matrix is 2 by 2, the vector is 2 by 1. So this concept that I'm telling only is applied only for this case, the special case of 2 by 2. We can have n by n in the general case, but right now we only want to focus on 2 by 2 or the vectors as 2 by 1. Now this x1, x2 plane that we talked about is also called a phase plane. So x1, x2 plane, also called the phase plane. Now remember, the goal is that we have a, let's say, system of ODs. We also have the initial condition, and we want to know how the solution behaves without finding the solution. We want to know as t goes to infinity, what does the solution do? Does it approach 0, for example, or does it approach to infinity? And the solution has two coordinates, so it could approach to 0 and 0, or it could approach to 0, infinity and 0, for example, or infinity and minus infinity, or infinity and infinity. So what does it, how does it behave, the solution? Without, of course, one way is to find the solution and then let t go to infinity, find the limit. But we want to find out about the behavior without finding the solution, only using the graph. So remember, initially at t equals 0, right? Initially at t equals 0, we are at x of 0, which is supposed to be b, and let's say this is some fixed vector b1, b2, right? Now let's say what happens at t equals 1? Where will we be? So if I know about the velocity of the particle, as if you imagine a particle at t equals 0, it's located at b1 and b2. Now, if I know about the velocity, if I know about the direction of velocity, I can estimate the location of the particle at t equals 1. Let's say if you have a particle, for example, here, let's say at 1 and 1, for example. And if I tell you that the particle moves along this direction, then at, let's say, 1 second later, you expect the particle to be somewhere around here, or could be here, depends on how fast it goes, right? But you wouldn't expect the particle to be, for example, here. Or you wouldn't expect the particle to be here. So it's important to know about the direction of velocity and direction of movement, because that helps us to estimate the location of the particle at t equals 1, and then at t equals 2, and so on. And then we can continue this process until we estimate the location of the particle as t goes to infinity. So here we have the location at t equals 0, and then the velocity at t equals 0 is x prime at 0, which is a times x of 0, and x of 0 is b, so it's going to be a times b. So this velocity, the direction of velocity, helps us to estimate the location of the particle at t equals 1. Say the estimated location is, let's say, B1. And then again, once we know that at t equals 1, the particle is at B1, again, if I know the velocity at that moment, I can use the velocity, the direction of movement to estimate the location at t equals 2, and so on. So then at t equals 1, the velocity will be x prime of 1, which is a times x of 1, and this is, let's say, a times b1. So use this to estimate the location of the particle at t equals 2, and so on. So just to get an example, let's say if you have x prime equals ax with, let's say, x of 0 equals 0. Let's say if originally the particle, I have a particle, let's say originally is located at origin, 0 and 0. And then I want to know what happens to this particle as t goes to infinity. So this is the original location of the particle. So initially, our particle is here. Then what will be the velocity at this moment? X prime of 0 according to, because I know that x prime is always a times x. A is a fixed matrix. So once I know x at some t, then I can find x prime at that t. So that means this relation, this equation gives the relation between the location of the particle at some specific moment and the velocity of the particle at the same moment. So at t equals 0, I'm assuming that the particle is at origin. So what will be velocity at t equals 0? X prime of 0, according to this, is a times x of 0. X of 0, I'm assuming it's 0. A times 0 is 0. So if the particle is originally located at origin, the velocity will be 0, which means the particle will be stationary at that moment, at that point. So the particle will have no movement and it will stay at origin. Such a point is called the equilibrium point because it remains there. So it's called the equilibrium point. So definition, the equilibrium point of x prime equals ax is the point where x prime equals 0. Because the particle, if you locate a particle there at the equilibrium point, it will stay there. So note that if A is invertible, Then if I have x prime equals 0, that means ax will be 0 because x prime is ax. That means ax is 0, and if a is invertible, I can multiply both sides with a inverse. Then I'll get a inverse times ax equals 0, and then that will give me x equals 0. So this is the equilibrium, the only equilibrium point, the only or the unique equilibrium point if A is invertible. So if A is invertible, our system will have only one equilibrium point, and if you locate the particle there, it will stay there. So at equilibrium point, as t goes to infinity, so note that if x equals x0 is the equilibrium point, and the particle is initially located at x equals x0, then as t goes to infinity, x will be still x0. The particle stays at that point. So remember, our goal was to find out about what happens as t goes to infinity. If I initially locate a particle at a specific point, as time passes, how does that particle move, and what happens to it as t goes to infinity? Where will it be located? Well, we saw that if the particle is initially located as equilibrium point, it will always stay there. It won't move, and as t goes to infinity, the particle will stay at that point. Now, in the next case, we can consider the case where the particle is located at one of the eigenvectors. So next, if the particle is initially located at, let's say, x of 0 equals, let's say, C1, where C1 is the eigenvector corresponding to the eigenvalue, let's say R1. Now, how does the movement look like in that case? So we know in order to find out about the movement, we have to look at the velocity, and we know that the velocity x prime at any moment can be found by multiplying a with x at that moment. So initially the velocity can be found as a times x of 0, and x of 0 we are assuming is c1. So then we can write this one as a times c1. But I'm assuming that c1 is the eigenvector with eigenvalue r1. So I can write this one as r1 times c1. So that means the velocity is also in the direction of c1. So initially the particle is in the direction of c1, And the velocity is also in direction of c1. So that means the particle remains in the same direction. So let's say if this is c1, and this is the direction of c1, so the velocity is in the direction of c1. So the particle remains in the same direction, which means that, let's say after some t, let's say at t equals 1, the particle still is the direction of c1. So I can say that the location of the particle is, let's say, some constant times c1. So at t equals 1, the particle location will be, let's say, some alpha times c1. Same direction as c1. So that means that the velocity at that moment, then x prime of 1 will be a times alpha c1, which is alpha times ac1. And this is alpha. AC1 we just saw. AC1 is R1 C1. So this is R1 C1. So still we are in the same direction. The velocity is still in the direction of C1. Again, in direction of C1. So we can repeat this argument, right? So if initially the particle is in the direction of C1, velocity at that moment will be also in the direction of C1. After some time, again, it will be in the direction of C1. After some more time, again, still in the direction of C1. So the velocity always remains in the direction of C1, which means the particle will be always in the direction of C1. Now, the direction of C1 means along this line. Let's say if C1 is in this direction, means along this line. Now, what along this line? Does it go farther from origin along this line? Or does it get closer and closer to origin along this line? Well, that depends on whether this R1, the eigenvalue, whether it's positive or negative. So we can say that by repeating this argument, we can conclude that. So let's say case 1, if R1 is positive and the particle is initially located at C1, then as t goes to infinity, the particle remains in the same direction and gets farther and farther from origin. If R1 is positive, then velocity at this moment, because the velocity is R1 C1, so if R1 is positive, velocity will be positive. So velocity will be this direction, getting far from origin. After some time, again, because R1 is positive, again, velocity will be still in the same direction, getting far from origin. So the particle gets farther and farther from origin, and it's going to move along this line farther and farther from origin. Also, if originally the particle is located in this direction, let's say minus c1, then the velocity, if originally it's at minus c1, you can show that the velocity will be still negative, again getting farther and farther from origin. So if R1 is positive, regardless whether you start from, let's say, some point at C1 or minus C1 or any point along this line that you start with, the particle gets farther and farther from origin as t goes to infinity. And similarly, in the second case, if R is negative, if R1 is negative, and the particle is initially located at, let's say, C1, then what happens? Then the particle, then as t goes to infinity, again, the particle remains in the same direction, but this time, gets closer and closer to origin and gets closer and closer to origin. So see, if R1 is negative, let's say if initially the particle is located at C1, then the velocity at t equals 0 will be a negative number times C1, which means the velocity is in the same direction, but towards origin this time. So the particle starts moving towards origin, and let's say at t equals 1, it's going to be at some point around here, and still the velocity will be negative, which means towards origin, and again gets closer and closer to origin as t passes by again repeating this argument. So if I want to sketch the graph, in this case, if the particle initially starts from here, then gets farther and farther. If it starts from here, it gets farther and farther. And also here, if let's say it starts from here, gets closer and closer to origin, or starts from here, gets closer and closer to origin. So no matter whether the particle starts from this side or this side of origin, the factor that determines whether the particle gets closer and closer to origin or farther and farther from origin is the sign of the eigenvalue. If it's positive, gets farther and farther from origin, regardless whether it starts from this side or this side. And similarly, if the eigenvalue is negative, you will get closer and closer to origin, regardless whether you start from this side or this side. So we can say that if we have a matrix, let's say with two positive eigenvalues, with the corresponding eigenvectors, let's say C1 and C2, then we can say that we'll have a picture like this, let's say. So let's say this is C1, and let's say this is C2. We just mentioned that if the eigenvalue is positive, then you'll get farther and farther from origin. So you'll get farther and farther from origin, whether you're here or here, get farther and farther from origin. Again, here you'll get farther and farther from origin. And So this is if you start from some point along this line or some point along this line, then we know how the particle will behave as t goes to infinity. But what about if the particle starts from some point in between? It doesn't have to start from some point on this line or some point on this line. It could start from some point in between. Then how does it behave as t goes to infinity? So say along any other point other than the points on these two lines, the particle will not stay on a straight line anymore, because the only direction on which it remains on the same direction is the direction of eigenvectors. So let's say if it starts from somewhere here, because it's not on the direction of eigenvector, it will not remain on the same line. It will move, but because this is here very close to this line, it will remain close, and it will move this direction and this one, you know, from this direction. We can say that if the particle is a little bit upper or higher, it will be close to that direction, but not on the straight line anymore, on a curve. So this is how the particle behaves depending on where it starts. So the particle, as we can see, if the matrix has two positive eigenvalues, it will get farther and farther from origin, regardless of the point where it starts. So in this case, we say that the equilibrium point, which is the origin, we say it is unstable, because if you remember the definition of stable or unstable, because, you know, if the particle is at equilibrium point or is at origin, it remains at the same point. But if the particle, the initial location, is disturbed just a little, then as t goes to infinity, the particle gets very farther and farther from origin. So in this context, in this sense, it is unstable, because just a little bit disturbance on the original location of the particle will lead to the particle getting farther and farther from origin as t goes to infinity. So let me mention about the definition of stable versus unstable here. Definition. An equilibrium point is called stable if a small disturbance, when the initial location of the particle is slightly disturbed, then as t goes to infinity, x of t approaches to the equilibrium point. And if an equilibrium point is not stable, then it is called unstable. So stable would occur if any slight change in the initial location, the particle as t goes to infinity goes to the equilibrium point. In this case, the equilibrium point is origin. So it would be stable if any slight change in the initial location, the particle still approaches to origin as t goes to infinity. But it is not the case here, because as t goes to infinity, let's say if the particle starts from here, it gets very far from origin as t goes to infinity. If it starts from here, again, it gets very far from origin. If it starts from here, again, see, it gets very far from origin. So it is not stable. The equilibrium point is not stable in this sense. Now, similarly, if the matrix has one positive and one negative eigenvalue. So previously we saw the case where the matrix has two positive eigenvalues. This would be the phase portrait. Then if it has one positive, one negative eigenvalue, say R1 positive with the eigenvector, with the corresponding eigenvector C1. Eigenvector C1, and let's say R2 negative with the corresponding eigenvector C2. Then how does the phase portrait look like? So this time we have two directions. And let's say this is C1, let's say this is C2. C1 is corresponding to a positive eigenvalue, so we'll get farther and farther from origin. C2 is a eigenvector with corresponding eigenvalue R2, which is negative, so we'll get closer and closer to origin. And in between, the graph looks like this. We have to look at these arrows to decide how the between these lines would work, you know, if the particle starts from somewhere in between. Because here, this is this direction, so it moves this direction. And then at the end, it will get close to this line. And this is getting farther from origin, so this has to be consistent with this. So this will also get farther from origin. Similarly, this has to be consistent with this. Remember, there's going to be a curve, not a line. So the only lines that we have are the directions of eigenvectors. And if the particle starts anywhere else, it will not stay on a line. It will be on a curve. And similarly here. And also here. So this is how the phase portrait look like. So we can use this to determine the trajectory of a particle, how the particle moves as time passes without solving the equation algebraically. Of course, one way to find out how the particle moves is to solve it algebraically. Once I have x of t, then I can find x of 5 or x of 10 or x of t as t goes to infinity. But what about if we don't want to spend time to solve the equation? Still, if we have access to this phase portrait, we can predict how the particle moves as t goes to infinity or as time passes. So for example, if let's say the particle starts from here, if the initial location is here, then we know that the particle will move along this curve, and as t goes to infinity, will be somewhere here, very far from origin and close to this straight line. Or let's say if the initial location of the particle is somewhere here, we know that the particle will move along this curve, and as t goes to infinity, the particle will be somewhere here, again, very far from origin and somewhere close to this line. Now, is this equilibrium point stable or unstable? Well, if we think about the definition, we have to see if we slightly change the initial location, does the particle get farther and farther from origin or closer and closer to origin? Well, this is the equilibrium point, which is origin. If we slightly change the initial location in this direction, let's say in this direction, then the particle as t goes to infinity will get closer and closer to origin. But if we slightly change in this direction, then the particle will get farther and farther from origin. Or let's say even this direction, it will get farther and farther from origin. Let's say somewhere around here, for example. So the equilibrium point is unstable because it would have been stable if any slight change in the initial location would lead to the particle getting closer and closer to origin as t goes to infinity. So this condition has to be valid for any slight change, any type of slight change, if we want to have the stable equilibrium point. If for some slight changes, you get farther and farther from origin, some slight changes closer and closer to origin, then still we would call the equilibrium point unstable. So we can say that note that the equilibrium point here, the equilibrium point, which is origin, is unstable since a slight change in the initial location in the direction of, let's say, C1, since, let me say, with a slight change in the initial location in the direction of C1, we will have x of t getting farther and farther from origin as t goes to infinity. So this is the phase portrait. If we have one positive eigenvalue and one negative eigenvalue. This is the phase portrait. And similarly, this one was phase portrait. Now we did for the phase portrait for the case where we had two positive eigenvalues. Phase portrait in the case where we had one positive, one negative eigenvalue. And finally, we have to do the phase portrait if we have two negative eigenvalues. So lastly, if the matrix has two negative eigenvalues, say R1 and R2, with the corresponding eigenvectors C1 and C2, then the phase portrait looks as follows. So again, I have two directions. And both of them this time negative. The eigenvalues are negative. So now let's say this is C1 and let's say this is C2. Both of them negative eigenvalues. So in both of them, I'll get closer and closer to origin. And so this is in the case where the initial location will start from somewhere along this line, then you'll get closer and closer to origin, whether you start from this side or this side. Similarly, because this one also has a negative eigenvalue, if you start from somewhere along this line, whether this side or this side, you'll get closer and closer to origin. Similarly, if we start from somewhere in between these lines, again, we know that the particle will not stay on a straight line. Instead, it will be on a curve, and the arrows on the curve and the shape of the curve should be in a way that's consistent with these two straight lines that we have already determined. So let's say if the particle starts from here, it will move towards origin this way, which is, and these arrows are consistent with these, and this is consistent with this. Again, this is consistent with this, and this is consistent with this. And similarly, so see, if we start from anywhere between lines, still we will get closer and closer to origin, we'll approach to origin. So in this case, as you can see, if we slightly change the initial condition in any direction, so let's say this direction, somewhere in between, somewhere in this between, or this between, this between, no matter how you slightly change the initial condition, as t goes to infinity, the particle will get closer and closer to origin, and therefore the equilibrium point in this case, for the first time, it's stable. So note that if we slightly change the initial condition, if we slightly change the initial condition from origin in any direction, as t goes to infinity, the particle will get closer and closer to origin. Hence, the equilibrium point which is same as origin, is stable in this case. Okay, guys, so we saw how the particle will move, and in particular, what is the behavior of it as t goes to infinity. How does it move? Is it going to getting closer and closer to origin, or getting farther and farther from origin? And if so, along which direction? So we saw different possibilities for different matrices. We considered three major cases: a matrix with two positive eigenvalues, one positive, one negative eigenvalues, and two negative eigenvalues. And we saw only in the case of two negative eigenvalues, no matter where the particle starts from, as t goes to infinity, will get closer and closer to origin. Therefore, the origin, which is the equilibrium point, is stable in this case. But in the previous cases, so in this case, along this direction, get closer and closer to origin, along this direction, or in between, get farther and farther from origin, overall is unstable. And in this case of two positive eigenvalues along any direction, we'll get farther and farther from origin, so unstable in that case as well.